to section 4.4, which has the intimidating title, Interpreting Graphs of Exponential and Logarithmic Functions. Wow, that's a long title. So in order to do this section, we're going to need a graphing calculator. So I have a graphing calculator right here, and I'll be giving you a graphing calculator in class to use. I'm also have another graphing calculator here. This is the Desmos graphing calculator, which you can actually get a free download on your iPhone. I'm not sure about Android, to be completely honest, but I would imagine so. And I also have a scientific calculator we're going to use. So we have lots of technology here that we're going to be using. The other thing is, usually I don't do this, but I've taken the questions from the class examples that are in the workbook. Often I leave those for you to do or for you to refer to. So just to let you know. Alright, the first question. In 2012, the university population of a country was 160,000. So I guess there's 160,000 people in the country who are attending university at that time. And it was increasing at an annual rate of 4.5%. The growth in the university population can be represented by the exponential function p equals 160,000 times 1.045 raised to the n exponent, where p represents the university population of the country as a function of the number of years n since 2012. Okay, so this is quite a mouthful, this question here. So what we have to do is determine the population in the year 2015. So remember, this amount right here, this 160,000, that's how many people there are in 2012. We want to know how many people there are in 2015, and remember that n is the number of years since 2012. So in this case, if we're interested in 2015, what does n equal? N is equal to 3, because 2015 is 3 years after 2012. So there's two ways you could answer this question. One way, the way that I think makes most sense, especially if this was the only question you had to answer in this question, would be to just plug 3 into the n. So you'd have p equals 160,000 times 1.045 raised to the third power. And you could figure out what that equals, and you would have the population. So remember, if you're going to do that, you're not going to do 160,000 times 1.045 first. That's a multiplying step. You have to do the exponent first. So let's go to the scientific calculator, and we will do that. So it's 1.045 raised, this is my raised, to the third power. I'm going to get that answer, and then I'm just going to multiply that answer by the 160,000. And we get the answer, oh, interesting, we're going to have a decimal answer. That makes no sense. So why don't we round it? So this would be 182,587. 182,587. Okay, there's actually another way we could answer this question, and it involves actually graphing this function here. And we might as well do that because we're going to eventually need to graph it in order to answer the second part. So first of all, when we graph on our graphing calculators, we don't have options to put p and n in there. So what we're actually going to be graphing, just so we're clear here, is y equals 160,000 times 1.045 to the, not n, but x. So I'm going to do this on the TI-83, and I'll be giving you these in class. So I click on y equals, and I want to enter that 160,000. I'm sorry, it's hard because the buttons are off. So there's the 160,000 times, so I'll put a bracket here, 1.045. Oh, I know this is painful to watch, isn't it? It's so slow. Close that bracket, and then we need to raise that, so there's my raise button again, to the x power, and you hit this button here for all the variables. So there you go. Now before we plot this, we need to think about this. If you just were to hit graph right now, probably nothing will show up, and the reason for that is because you have to set the window, and the window, you have an x minimum, x maximum, y minimum, y maximum. You want to set those. So the x minimum, remember x is actually what n is, which is the number of years after 2012. So we're not interested in anything before 2012. So what would probably be the lowest amount we'd want to have here? Probably 0. In other words, when there's no years after 2012. Okay, now we'll go down to X max. What's the most years you'd want to look after? I don't know, maybe 30 years or so? Probably don't need any more than that. So we'll put 30 in there. Okay, now the Y minimum and Y maximum, this is the number of people. Well, it's never going to go, it says that the population is always increasing. So if it started at 160,000, we don't even need to go below that. But why don't we go a little bit below that just so we can see the curve nicely? We'll put 150,000. I'm using my keyboard to click these in, it's a little bit faster. And why don't we go up to about, I don't know, 200,000? There, and now we'll hit graph and we'll see what it looks like. Hopefully we pick some good amounts. Not the greatest actually, but we can still use it. And what I want to actually show you is if you know the X value you're interested in, remember our X value was 3, then what I can do is I can hit second trace, because by hitting second trace it's actually the yellow one up here, the calculate, and I want to know a certain value, so that's number 1. So I hit 1, and the value I'm interested in was when X is 3, right? 3 years after 2012. So if I just put 3 in there and hit enter, I get that when X is 3, in other words after 3 years, the population is 182,587, and that's exactly the amount that we already found right here. So that's a second way you could also get the answer. Okay, the next one, it says determine the number of years required for the population to double from its 2012 size. So in other words, we're going to use the same formula, but this time we know what the final population is. The final population is going to be double of what it started with. So it's going to be 2 times 160,000 is 320,000. So what we have to do is we have to solve, if you plug the 320,000 in there, you get 320,000 equals 160,000 and then 1.045 to the n power, and we have to figure out what number goes right there. Now if you were going to try to do this without a graphing calculator, it's very difficult. You'd have to use guess and check, or I'd have to teach you even more about logarithms, about solving equations with logarithms. It's not terribly difficult, but I don't think we want to spend the time doing that. So what we'll do here is we'll use a graphing calculator. The graphing calculator is your friend here. So we want to know when the population is up to 320,000. So first of all, I think you'll agree with me, when I did the windows, I made a mistake because I only wanted to 200,000. We wanted to know when it's at least 320,000. So why don't we put like 350,000 in there and regraph that and see what we get. Okay, good, that looks nice. So now what we're looking for is where's the point on this where the population's doubled? In other words, where the Y amount is 320,000. Well, I don't know exactly where it is, so here's what I do. I go back to the Y equals, I go down to Y2, and I put in 320,000. What will that make on my graph? If you just have the equation Y equals 320,000, what kind of line will that make? I'll make a horizontal line where all the Y values are 320,000. There you go. These are the spots where all the Y values are 320,000. Well, that's the spot we're interested, because that's where it crosses the actual curve. So we want to know what's that spot right there. So here's how you do that. If you want to know where they cross each other, you do the following. You hit second again and trace again to do the calculate. But you're not getting a value this time, you're getting an intersection. So you're going to hit number 5. And what it says is first curve. And you see this little blinking thing here? I was lucky enough that it actually showed up on one of the, I can actually see it. So all I have to do is hit enter. And once I hit enter, it should jump to, yep, now it's on the other one. If you want, you can move it a little bit just to make sure it's on the other one. So I'll hit this arrow. Yeah, it's definitely on the other curve, or the other line in this case. So I hit enter again, and then it says guess. So now what I'm going to do is I'm going to guess, in other words, put the thing as close as I can. So I'm hitting this arrow, and that looks about where it belongs. And I hit enter, and it will tell me, it's thinking, that the intersection, you can see the Y amount is 320,000, that's what we wanted, and it says the X amount is 15.7. So after 15.7 years, the population will have doubled. And I think in your book, it actually asked you to the nearest whole year, so it'd be 15.7 years, which is approximately 16 years. That would be your answer in this case. The number of fish in a lake is decreasing by 5% each year as a result of overfishing. The number of fish present after t years is given by the formula n of t is equal to n original times 0.95 raised to the t power, where n original represents the initial population and n of t represents the final population. there were 2,500 fish present in June 2012. Determine how many fish you would expect to be present in June 2017. So again, we're interested in 2017, and this started at 2012. So our T amount in this case is 5 years. We're interested in 5 years later. So once again, you could take that 5 and just plug it in right there, and you could get your answer. So I'll leave that for you to do that, but let's do this by the graphing method, because you're going to have to anyways graph it to get the second one. So let's see, we're interested in when the fish population reduces in half. So we want to know in this question here, just to kind of set them both up at once, we want to know when the fish population is equal to half of 2,500, and half of 2,500 is 1,250. So let's go to the calculator. We're going to enter in this right here, but of course it won't be n of t, it'll be y. N original, well, we now know n original. N original was 2,500. 0.95 raised to the, not the t, we're going to call it the x. So this is what we have to enter into the graphing calculator. So bring that up, hit y equals. Maybe we'll get rid of these by hitting clear, and we'll get rid of this other one by hitting clear as well, and go back up to y1. So we're going to enter in 2,500. I'll do it with the keyboard, it's a little faster. For some reason you can't use the keyboard on this emulator for bracket, so there's my bracket. 0.95, close that bracket, raise that to the x power, so this button right there, and that is graphed. Now window, let's go to our window. So in terms of time, we're interested in years passing by. We could try 0 to 30 years. I think that's probably okay. Now y minimum maximum, this is definitely going to be way too big. Why don't we put the minimum at 0, so when the fish population is decreasing, so it might go all the way down to 0 unfortunately, and the highest the population was in this question was 2,500. Why don't we put 3,000 just so we have a little room to work with, and we will hit graph and we'll hope for the best. You know, it is, unfortunately, sometimes you guess wrong and you have to go back and change the window. It can be a bit of a drag, but this looks pretty good. I think this will work. So remember, the first question is determine how many fish you would expect to be present in June 2017. We said you could either take that 5 and put it into this spot right here and just solve it that way. But if you're being, I don't know if it's lazy is the right word, but if you don't want to do the calculations, you could go to your graphing calculator. You could put second, trace, we want to know the value, and we want to know the value when x is equal to 5. So you put 5 in there and hit enter, and you get, when x is 5, y is 1,934.4. I don't think you're going to have half a fish, so we'll just put 1934. Great. The other question we're interested in is when will the population be reduced to 1,250? So again, I don't know where 1,250 is here, but what I can do is set up a line that will show me. So I go down to y2 and I put 1,250 and hit graph, and I'll have exactly the same thing, but now I know this is exactly the spot I want right there. So I'm going to do second, trace. I'm looking for an intersection, which is number 5. It says first curve, so I can't tell what curve it's on. I'll hit one of the arrows. Okay, good, it's on the actual curve. I'll hit enter. It should jump to the other one. Yep, it looks like it's on the line. If I move it a little bit, it's definitely on the line, so I'll hit enter, and then it says guess, so I'll move it over to about the best spot I can get, which is about there, and I hit enter one last time, and it will tell me that y is equal to 1,250 when x is 13.5. So after 13.5 years, the population will have reduced in half. Again, in the book it might ask you to put to the nearest year, so 14 years. Okay, third one, in chemistry the pH of a solution is defined as pH equals the negative logarithm of H plus with these square brackets, and if you take chemistry you know those square brackets mean concentration. So this is the hydrogen ion concentration expressed in moles per liter. So if you want to know the pH of a solution to the nearest tenth, if the hydrogen ion concentration is 3.4 times 10 to the negative 4, all you need to do is put that in here. So what the heck, we'll do it that way this time. pH equals the negative logarithm of 3.4 times 10 to the negative 4. And by the way, 3.4 times 10 to the negative 4 is the same as 0.00034 because you're moving that decimal 4 spots to the left. Okay, I'll use my scientific calculator to do that. So I'm going to leave the negative off for now. I'll add that at the end. I get 0.00034. I'm taking the logarithm of that. If I do that, I get negative 3.5. And remember, it was actually negative that, so it's actually positive 3.5. I would put the negative at the front, but for some reason the calculator glitches when I do it. So remember, it was actually negative in front of here, and negative negative makes positive. So our answer is 3.5. pH equals 3.5. Okay, the next one, if a patient gives a urine sample and it has a pH of 5.7, what's the hydrogen ion concentration? So again, this is very difficult to figure out without using either solving with logarithms or to actually graph it. So let's actually graph it. What we'd be graphing is y equals negative log of x. That's it. That's all we'd be graphing. So let's do that, but let's do it this time in Desmos. It's a little bit faster. So we get y equals negative, the logarithm sign is down here, right there, of x, and I'm going to graph that, and there it is. However, we're interested in when the pH is 5.7. So just like before, what you can do is you can put another one and put y equals 5.7. And you can see it's way up here and it's very hard to read. So what we might want to do is expand it. We could keep zooming in and zooming in. You can definitely do it that way. Or the other way you can do it is you can click on the graph settings and you can change it. So it looks like we want our x-axis to be very, very small. So why don't we say our x-axis is going from 0 to 0.00001. How's that look? That's looking okay. We can actually see the intersection point. The nice thing about Desmos is all you have to do is click and drag, and you can see right there, you get your answer. And what the answer is 0.000002. So I think we're supposed to give this answer in scientific notation. Do you know how to do scientific notation? I'll write it both ways. So it has 5 zeros and then a 2. 0.000002, which is the same as 2 times 10 to the 1, 2, 3, 4, 5, 6 to the negative 6, and this is in moles per liter. So this is your answer. Okay, last one, thank goodness, is taking too long. The decay of radioactive elements can sometimes be used to date events from the Earth's past. In living organisms, the ratio of radioactive carbon, carbon-14, to ordinary carbon remains fairly constant. However, when the organism dies, no new carbon is ingested, and the proportion of carbon-14 decreases as it decays. An estimate of the age, x years, of organic remains can be determined from the exponential function p equals 100 times 1/2 to the x divided by 5,730, where p is the percentage of carbon-14 remaining. Wow. So if the skeleton of a bison is about 10,000 years old, and we want to know what percentage of carbon-14 should be found remaining in its bones, then what you would do is you'd put that 10,000 into the x right there. Okay, so again, you could do that with your calculator, or we could just graph this. Let's graph it. So we would have p equals, oh, except it's not going to be p, is it? It's going to be y equals 100. Instead of 1/2, let's make it 0.5, raised to the x divided by 5,730. So let's do this on Desmos again. We have, get rid of both of these, we have y equals 100 bracket 0.5, then you got to raise that, so you use this button here for raising something to a power, and then we want x divided by, look at how nice Desmos is, it makes it a fraction, 5,730, and we'll hit return, and you can see nothing here, and the reason for that is because it just doesn't fit on the graph, so we need to change our window. Remember, the x value we put in was 10,000. We're interested in what's 10,000, so we definitely want to have huge x values. Why don't we put x going from 0 to 50,000 maybe? And this looks much better. We now can see the graph pretty nicely. we want to know in this first question, if the bison skeleton is 10,000 years old, how much carbon-14 is there? So the x value is 10,000. So we go to 10,000 right here, and we go up until it reaches the curve. So I'm moving up, I'm moving up, I'm moving up. This is it right here, and you can either click on it, and you can get it that way. It's a little finicky, but you can definitely do that. Or the other thing you can do, and this is nice about Desmos, you don't only have to have y equals, you can also put x equals. So I'll put x equals 10,000, and now you have the exact spot right there. It's 10,000, comma 29.8. So 29.8% of the carbon-14 should be left. 29.8% is our answer. And the final question, if the carbon dating test indicates that approximately 20.3% of carbon-14 is left in a bone fragment, estimate the age of the fragment. So this is our y value this time. The y value is 20.3. So we can go back here, we can put y equals 20.3, and we're going to find where it crosses. Well, 20 must be down. There it is. 20.3 is right here. And you look to see what the intersection point is. It's so much faster in Desmos. I love it, and it's free. And you get 13,182. So there you go, 13,182, but they wanted it to the nearest 1,000 years, so it'd be 13,000 years. Alright, there you go. I'll give you graphing calculators in class. I recommend you download Desmos as well, and then you also can use your scientific calculators or pen and paper. Up to you.
Tears and the sadness you gave me, you put the hurt on me, you socked it to me, mama, when you said goodbye.